the inverting configuration. So in the past, when we used the op amp, as all of the previous examples that we've learned so far, the op amp, is this triangle. V3 is the output, V1 and V2 are the input. So this is called, actually there's a name for using an op amp like this. This is called open loop configuration. So what is meant by open loop configuration is that there's no feedback. Feedback would entail some kind of connection going from the output feeding back to the input. But so everything we've learned so far, it did not have any kind of feedback involved. But this kind of configuration actually has no, we do not use it because it has stability problems. It is not possible to be controlled easily, and it may also oscillate, so it's not stable, it's not controllable, so we don't use open loop configuration. Instead, when we use op amps, so when we use op amps, we usually employ feedback. So feedback is what we'll talk about first. So an example of feedback would be like this. So we have our op amp, the triangle, we have the output, and we have the input. So it's called a resistor here is R1, and we connect that to ground. We send our input to this positive terminal, and then we have a what's called a feedback resistor, and this is called at R2. So this is an example of feedback because a portion of the output is being fed back to the input. Now I'm going to copy this circuit, and I'm gonna reuse the same circuit, but I'm just gonna make one modification. Let's flip the op amp to go upside down. So now the plus is on top and the minus on the bottom. This is another type of feedback. In fact, we have a name for this. So the left side is called negative feedback, and the right side is called positive feedback. So what is meant by this negative and positive feedback? Okay, so in the case of negative feedback, the output is being fed to the negative terminals, hence the name negative feedback. But in the case of positive feedback, a portion of the output is fed back to the positive terminal. This is why we call it positive feedback. So there are two types of feedback. There's positive and negative feedback. Okay. Feedback is a very revolutionary concept when it was invented at its time. This is like 1920s because it allowed the circuit to have better stability, better control of the gain, and so it was a very revolutionary concept. The original use of feedback would be this positive feedback configuration, but positive feedback today is very rarely used. We don't use it very often. This is very rare. So it's very rare. And the reason why we don't use positive feedback often is because positive feedback has, if the conditions are not very tightly controlled, there will be instability. There might be some difficult to control, so we don't really use the positive feedback that much, except for some very, very tightly controlled applications that take advantage of the instability, like maybe you're trying to make an oscillator to generate the sine waves. In that case, then maybe positive feedback is used. But like 99% of the time, we are talking about this negative feedback. Negative feedback is way more common because the circuit is way more stable, and the circuit is very predictable output. So we use negative feedback. Now, within negative feedback, there are two configurations. Actually, let's talk about this. So we have op amp. We can use the op amp either in open loop configuration or with closed loop called feedback. And within feedback, there's negative feedback. There's also positive feedback. And even within negative feedback, there are two more configurations that we learned about. The first is called inverting configuration, and the other is called non-inverting configuration. But today we will study inverting configuration. Later we talk about non-inverting. So within negative feedback, we have inverting and non-inverting configuration. But we first study inverting today. So what is an example of inverting configuration? So I'm going to give an example circuit to demonstrate this. So we have the op amp, obviously. Let's draw that a little good. Okay, we have the op amp and we have the output, and inverting configuration is a type of negative feedback. So we are connecting the feedback to the negative terminal using a feedback resistor, and then we connect this positive input terminal to the ground, and then we have a input resistor here, and then we connect V in to the input. Now what actually is the definition of V in is in reference to ground. So we have our V in like this, and it's in reference to ground. So this is actually how we're doing it, and a V out is measured in reference to ground. So this is called, in your textbook, is called figure 2.5, which talks about the inverting closed loop. Closed loop means it has feedback, and it's in this case negative feedback configuration. This is an example of inverting configuration. Now, just to review what we learned in the ideal op amp. The ideal op amp, everything still holds here, where the output is V3 is equal to A, which is the open loop gain, multiplied by V2 minus V1. Actually, it's better that we call it V out is equal to A times V2 is the plus, so we call that V plus. Is the voltage here is called the V plus, and the voltage here is called V minus. Okay, so V plus minus V minus is equal to V out. So this is still holds from before. Nothing has changed here. But now you understand why A is called the open loop gain. Now you understand why we call it open loop gain, and it's because well, when the op amp is when the op amp is like in the individually like this, there's no feedback, or the gain here would be A. A is the gain. It's the open loop gain. There's no feedback. When it's by itself, it's this equation. Now you know why it's called open loop gain. But when we're talking about this whole circuit, not just the triangle, remember, open loop gain A is talking about the gain within this triangle only. This A, this gain within the triangle only. But now we're talking about the whole entire circuit. What is the gain of the whole entire circuit? We call this closed loop gain. And it's defined by G. G for gain is V out divided by V in. Okay, so now there's two kinds of gains that we must talk about. Remember, there's an open loop gain A, which is just the triangle by itself. That's the gain of the triangle only. And then there's closed loop gain, which is the gain of the whole circuit. Whole circuit gain is called closed loop gain. So like before, so in the we just keep talking about the ideal op amp. So in ideal op amp, like before, we're not changing this assumption. We assume A is equal to infinity. Open loop gain is infinite open loop gain. So there is something interesting. So if V3 is equal to A times V2 minus V1, this is the equation from before. But what happens is if A is infinity, so there is some kind of problem like this. We know that V3 it's a finite number. So therefore, if V3 is a finite number, then V2 minus V1 must equal 0. So that infinity multiplies 0, you can get a finite number for V3. So, okay, so V2 minus V1 equals 0. In that case, you just say that V2 equals V1. So, in the ideal case, V1 equals V2. For the ideal op amp, V1 equals V2. Why? Because the gain is infinity. So an infinite gain means that V2 minus V1 has to equal 0, so that infinity multiplies 0 gets you a finite number. So due to infinite open loop gain, V minus is equal to the same voltage as V plus. In fact, there is even a name for this. We call this called virtual short circuit. Virtual short circuit is that in the ideal op amp, it is as if the two input terminals are shorted. We call that a virtual short. It is like a short. There's not an actual physical connection happening, but it's acting like a short. It's acting like a physical connection. So we call it virtual short. Now, in the case of our whole entire inverting configuration op amp circuit, in this case here, you can see that the positive terminal is connecting to ground. So in this case of this circuit, V plus is equal to V minus, which is equal to 0. The name for this is called virtual ground. So we call this a virtual ground. Now, let's do some circuit solving to figure out what is the gain of this circuit that we keep on talking about. So we know that from the ideal op-amp has infinite input resistance, which means that the current go through into the op-amp terminals to the input terminals, the current is 0. So if the input, there's no current going to the input of the op-amp, then the current through this branch must equal the current go to this branch. So we say that you can just do a KCL where I1 equals I2. Let's call this one I1, this one I2, because there's no current go into the minus, the negative input terminal. So we say the KCL, we can say V in minus V minus, so V in minus V minus divided by R1 is equal to V minus minus V out divided by R2. So now for the moment being, we assume this is ideal op-amp. So given virtual ground, then that says V minus is equal to V plus is equal to 0, because the ideal op-amp says that the voltage here equal voltage there. So given that, we say V in minus 0 divided by R1 is equal to 0 minus V out divided by R2. So then V in divided by R1 is equal to negative V out divided by R2. Then we say the gain, which is defined as V out divided by V in, is equal to negative R2 divided by R1. You just multiply it there and then divided by V in. Okay, so this is the definition of closed loop gain. Closed loop gain of the inverting configuration circuit. Okay, it's pretty simple. So let's do some practice problem. So let's say V in, we are told, equals sine omega naught t. It's a sine wave with frequency omega naught. And we are told that R2 divided R1 is equal to 10 ohms over, it's a unitless value. The question is, what is V out? Okay, so we say G is equal to negative R2 over R1 is equal to negative 10. So then V out, the gain is V out divided by V in, is the gain must equal negative 10, right? So just do gain multiplied by input is negative, okay, V out is equal to negative 10 sine omega naught t. Yeah, so it's pretty simple. So as we can see, V out is an amplified inverted form of V in. So that's why we're calling this inverting configuration, because it inverts the output. Now, I just want to make some observation for engineering. So since most people are electrical engineers, what's the one thing that we can consider is that gain, which is G, relies entirely upon passive components, which is R1 and R2, these resistors. So by adjusting the ratio of the resistor values, you can adjust the gain, the closed loop gain, to be more specific. So now we are no longer so up until this point we were talking about the ideal op amp which has infinite gain, but now we're going to talk about the real op amp where gain is not infinity. It's not infinity. The real op amp has a limitation on the open loop gain. So we call this a finite gain. Finite gain. Okay, be more specific. Finite open loop gain. So let's do another practice problem to address this. So actually this is section 2.2.2. It's called finite open loop gain. So let's talk about this. I'm going to provide we're going to provide the inverting configuration circuit. It looks something like this. So you have V in, you have input resistor called R1, and then we have the op amp, and then we have the positive terminal, it goes grounded. Then we have V out, and the negative feedback through the feedback resistor is called R2. So now we cannot assume, because this is a real op amp, we can no longer assume that the voltage at V minus is equal to the voltage at V plus. We can't make that assumption anymore, like the virtual short, called the virtual ground. We can't make this assumption anymore because it's no longer an ideal op amp. Now we're working with real op amps where the gain, open loop gain, is finite. Okay, but the same equations for open loop gain still hold. Is that V out is equal to A times V plus minus V minus. And we can clearly see that V plus is equal to 0 because it's grounded. So now we're just going to do some plug-in for V plus is equal to A, which is now a finite number, 0 minus V minus. So V out is equal to negative A times V minus. Now I'm going to solve for V minus, and says that V minus is equal to V out divided by negative V out divided by A. Yeah. Okay, so I'm going to save that because it will this equation will come in useful in a little bit. So now we're going to do the same thing as before. We're going to assume no current goes inside the op amp. It just so that so we know that the current here is equal to the current here because there's no current going into op amp. We're going to keep that assumption. So let's just do another KCL, just the same thing we did before. We say V in minus V minus V in minus V minus over R1 is equal to V minus minus V out divided by R2. Now do cross products. So R1 V minus minus V out is equal to R2 multiplied by V in minus V minus. We're going to sub this value for V minus. So it's R1. Let's change colors to represent this V minus, negative V out over A minus V out is equal to R2 multiplied by V minus minus negative V out divided by A. Okay. This is a positive sign here. A minus and negative becomes a positive sign. Okay. Yes, so let's continue solving for V out. In order to do that, you must distribute the R1. So negative V R1, okay, negative R1 multiply V out divided by A minus R1 V out is equal to R2 V in plus R2 V out over A. Okay. Okay. Yeah, we're trying to solve for gain, which is V out over V in. So let's move the V out. Every time we see V out, move to left side. Every time we see V in, move to the right side. So that's negative R1 V out divided by A minus R1 V out minus R2 V out divided by A. This is equal to R2 V in. So we can distribute out the V out, so it becomes V out multiply negative R1 over A minus R1 minus R2 divide A equals R2 V in. So divide both sides by V in and divide both sides by this kind of things here. So we can say gain is equal to V out. Okay, close to gain is equal to V out divided by V in is equal to R2 divided by a very complicated equation. Yeah, so now this is the answer. We have now figured out the gain of the op-amp when A, or open loop gain A, is no longer infinity, because now it becomes a finite number because we're dealing with ideal op-amp. But there is some useful things that we can observe if we manipulate through algebra to make this gain equation a little bit different. Now, Cedric Smith, the textbook, will just jump to the final result at the end, but it is very important, I think, that we solve it out, and so that we can profoundly understand how does the equations work. So you only need to do this once in your life, but it's very important that you go through the derivations. So we're going to do that right now. So instead of skipping to the final answer, we're going to just do some little bit of algebra here. It's not that complicated, it just requires some patience. So let's divide the numerator and the denominator both divided by r1. So now we have r2 divided by r1. We have 1 over r1, negative r1 over a minus r1 minus r2 over a. So now this equals to r2 divided by r1 divided by, let's distribute this negative r divided by r1, let's distribute this throughout. So it becomes so it becomes so actually this division that I'm doing is a little bit so it's divide the new top by r1, then that means that it is divided by r1. So what we were really doing is we're doing 1 over r1 divided by 1 over r1, like this. So that's the same thing, but I'm just being a little bit more specific. So now you have, it looks like this. So we're distributing this negative r1 to all three parts here. It becomes negative 1 over a minus r1 over r is 1 minus r2 over r1a. So all I did was I just divide the top by r1 divided by the bottom by r1. I just did those two things only. Okay, now let's do some simplify it by move the negative sign to the top. So negative r2 over r1 is equal to 1 over a plus 1 plus r2 over r1a. Now let's do a little bit of rearranging the denominator. We say this is 1 plus 1 over a plus r2 over r1a. Okay. Yeah. So let's just group this so that we can say is equal to negative r1 over r1 divided by 1 plus something. Let's make this a fraction that we can add these two fractions together. So it becomes the right side stays the same, but we have to do a r1a here, so that like this. So we are making the fraction capable of doing addition. So now we say negative r2 over r1 divided by 1 plus r1 plus r2 divided by r1a. Let's just do some just a little bit more massaging to this algebraic equation. So can you see that it becomes r1 over r1 is 1 plus r2 over r1. So I'm just dividing it by this r1, just moving the r1 to the top. So we're just doing this plus this, but we're distribute this negative r1. So okay, I will just specify it was r1 over r1, right? You just divide everything by r1, removing this r1 inside everywhere, so just 1 here. So yeah, so we're just moving the r1 to the numerator, just making it divided by r1. Okay, so dividing both terms by r1. So here's the another way of writing this gain, and you might be wondering, well, why do I care to write it this way? So that is a very interesting thing, because remember, as a goes to infinity, the op amp becomes more ideal. So let's say as the op amp becomes more ideal, we say limit as a goes to infinity over negative R2 over R1 divided by 1 plus R2 over R1 divided by A. So if you plug this as infinity here, then this whole term goes to 0. So 0 plus 1 is 1. So then it's just equal to negative R2 over R1. So as the op amp becomes more and more ideal, you start approaching this negative R2 divided by R1. Now, let's think about something a little bit more interesting. We have talked about in the past that V out is equal to negative A. It's inverting configuration, so it flips the output, so it becomes negative A multiplied by V plus minus V minus. So let's solve for, okay, actually, yeah, just to make things simple, let's just say A already contains the negative value, so it's just V plus minus V minus. Okay, this is V out. So now we can say V out divided by A is equal to V plus minus V minus. So then V minus is equal to so let's okay minus V minus is equal to V out over A minus V plus. So therefore, now remember V plus was connect to ground, so it's minus. It connects to ground, so it's 0. So now we say just move the negative sign to the other side, and leaves negative V out. Okay, V minus is equal to negative V out divided by A plus 0, which is V plus. So this is the V minus. So okay, why is that helpful? Well, you can see that as the limit of A goes to infinity, as the op amp becoming more ideal, so becomes negative V out divided by infinity becomes 0. So as the op amp becomes more and more ideal, this voltage at this V minus gets closer and closer to virtual ground. So this is the virtual ground assumption in the ideal op amp. Now it is very important. It is very important to design your circuit such that 1 minus R2 divided by R1 much smaller than open loop gain. You must design it this way, otherwise the op amp will not be working correctly.